Hello again and welcome. Today we're going to be looking at this KASUNTEST KT6000 meter. Notice on the front of this it shows it'll measure up to 20 amps. You can see between these two meters I have the KASUNTEST ZT102. Of course this meter has been damaged, but the 10 amp current shunt is still working. So what I have on the left here is a large power supply. This is set up as a current source. I also have a large shunt down here. This is 1 millivolt per amp, and the Bryman meter is stuck across it. And then this supplies the current through the duct, which in this case will be the ZT102. And then across that meter I have my UT181A. So the UT181A is looking at the burden voltage. The Bryman is looking at the current. So you can see currently we're outputting roughly 500 milliamps. And you can see down here this is our large shunt. And off to the left you may remember this power supply that I use this for testing the multimeter leads. So I've got this small computer set up to ramp the current. We're going to start with 500 milliamps. We're going to increment it by 500 milliamps every 5 seconds. And let's just see where this fuse pops at. You can see we've switched to 1.5 amps. And there's 2 amps. See, the burden voltage is going up quite a bit. Of course this thing is only dropping a millivolt to measure this same current with the shunt. This is normally how I'd be doing these measurements anyway. I don't typically use the current measurements of the meters. It's pretty good so far. We're at 7 amps. It's dropping about 210 millivolts so far. I've got the power supply programmed to put a maximum of 20 amps through this meter, so it should blow the fuse. You can hear the fans on the power supply starting to wind up as we're pulling a little bit more load off of it. It's 12.5 amps at 425 or so millivolts a drop across that. Oh, it just popped. That's almost 16, 17 amps. So I purchased this meter on Amazon for $37. This meter is also sold as an AN860B. This meter does have a few features that the little ZT102 did not. It has this min-max and this relative mode. You can see another feature is it has this microamp range for both DC and AC currents. I've looked at a few reviews of this meter online. One of the things I'm seeing is that they're showing that it can't read very high frequency, which is a shame because this meter can read about 200 megahertz. So I would expect this thing would actually read up that high. But a couple of people have tried it now and are getting similar results, so unfortunately it's probably the case that it really can't read it. So again, for input protection, you can see there are no MOVs. It has a small PTC up here, and again, just the 2 transistors for the high-speed clamp. It's a shame, but it looks like the PTC that they're using is actually a smaller body size than the one in the ZT102. Now this PTC actually survived all the testing. Typically when they get too small, the PTC will break down at the higher voltages and it'll crack this outside and it'll arc across. The other bad thing is you notice that the cheaper meter, this thing again costs like $15–20. We can see it actually has small ceramic fuses. This was again our 10 amp. But what are they using this? Glass. It's like, why do they do it? Oh, this is interesting. You can see on the circuit board, this is marked 10 amp, 250 volts. This is the manual that comes with the meter. And we can see maximum measurement voltage drop, measuring a range of 20 amps, is 200 millivolts. Maximum current, 20 amps for no more than 10 seconds. Overload protection, look at this, 20 amp, 250 volt fuse. And we see the same thing here for the AC over voltage protection, 20 amps, 250 volt fuse. So what the heck is actually in here? You can see right here it says F 20 amp L 250 volt. So it is a 20 amp fuse. The board itself is calling for 10 amp. And look at that little shunt. Looks like for the other fuse it's calling out 800 milliamps at 250 volts. And in this case it's a 500 milliamp fuse. And the manual is calling out a 500 milliamp fuse. Well, you got the usual split connectors. You can see how the battery clips are a little mangled on it. I'm sure the beeper is quite loud. Okay, we're ready to go. You can see I have the power supply attached in series with the KT6000. Again, I'm using this 1 amp per millivolt shunt, and the Bryman BM869 is looking at the voltage drop across that. And then the Unity 181A is looking at the voltage drop across the KT6000. So again, this is basically measuring the burden voltage. This is looking at the current, and this is also looking at the current with a 20 amp shunt enabled. The computer is set to sweep up to 30 amps, and again we'll do that with a 5-second hold, and we'll step by 500 milliamps. And again we can see the maximum measuring voltage drop with a range of 20 amps is 200 millivolts. So I'm not expecting this UT181A to ever read above 200 millivolts. Okay, let's go ahead and start the sweep. Again, this value is the current, and of course the current over here. They should all read roughly the same value. You can see we're at 3.5 amps right now, and we're already dropping almost 150 millivolts. There we are, so 5.5 amps, and we're already exceeding 200 millivolts. And you can hear the fan starting to wind up on the power supply as we're starting to pull a little bit more current. We're not going to exceed the capacity of this power supply, not with this test. Oh, so at 10 amps the KT6000 starts to give us a warning. Of course the Bryman with the shunt is not going to have any issues with this. See, we're dropping almost a half a volt now at 16 amps. Now, of course, they only rate the meter to handle 20 amps for 10 seconds. There you go, we're at 20 amps and it's still holding just fine, but it's dropping 3 times more than what they specify. So the control loop is having a little bit of problem, starting to drop some voltage. There, it opened up. So about 25 amps. That's pretty impressive. I'm sure all we did was damage the fuse in this. It definitely popped the fuse. I think something here was getting pretty warm. This has actually melted the fuse holder right there. So it's melted the fuse holder right into the standoff. These fuse clips are just really poor. They hardly spring at all. So this is a F10A L250. I don't have any 20 amp fuses. This would have came out of one of the other meters that I damaged. Meters back together. I'm all putting roughly 1 amp right now, and we're dropping about 30 millivolts across this meter. It's displaying roughly 1.01 amps. Let's just go ahead and we'll take this up to about 9 amps. And you can see no problem. It's 9.00. because we're reading 8991 or so on the Bryman, and our controller is roughly 9 amps as well. And I'm sure with the 10 amp fuse in there, it'll handle the 10 amps. Yep, right there it starts beeping again. You can see 9982.999. But again, we're dropping 316 millivolts right now, and again, this is rated for 200 millivolts drop with a 20 amp load. So yeah, it looks like the meter from the factory could read about 20 amps. You'll probably want to check to make sure that the clearances are okay around the area of the fuse though, before you start melting your case. So the meter included a few accessories. There's these small alligator clips. I would assume you could use these for component testing. Again, similar to the other meter, it looks like the leads themselves are quite short. And again, it looks like the same thermocouple is included with it. And of course the manual. Again, one of the things I noticed while watching some of the reviews for this meter was just how poor the frequency counter feature was. So you can see I'm currently in AC volts, and I've got the Hertz mode enabled, and I'm outputting roughly 9 kilohertz right now. And this is currently attached to my RF generator. I mean, this is like 48 kilohertz. Let me increase the power a little bit. Let's get rid of our 50 ohm terminator. So this is correct. This is 58 kilohertz. Right here it's starting to fall off. One of the things I noticed when I was looking in the manual is under measuring frequency, note this caution 1. In frequency measuring mode, there's only automatic ranging. So I don't think there's a way to put this thing into manual ranging mode, and that's probably why it's having this issue. So if we select the millivolt range, and we'll place this into AC mode, and then we'll look at the frequency. I imagine this will go up to quite a bit higher frequency, and that's what other people have also seen. Yeah, no problem. So this is 8.1 megahertz right now off the RF generator, and again that RF generator is sunk to the GPS, so this meter's off just slightly. What I'm going to do is reduce the RF level, and we'll see where it drops out at. So it looks like the meter falls out at about 10.5 dBm, but again that's without our 50 ohm terminator. This is pretty bad. So right now I'm putting out roughly 9.3 megahertz, but you can see the meter is very sporadic. This is 9.5 megahertz. Let me try the other RF generator. Maybe putting a little bit more power into it will help it pick this up. I can actually do better in some places with a lower amplitude than I can with a higher. So currently this is with 0 dBm, and it's able to read the 9.1 megahertz. Oh. So this is 10.27 megahertz. I'm actually reducing the amplitude, not increasing it. So currently this is with roughly 13 dBm, and again without the 50 ohm terminator. You can get into the 8 megahertz pretty reliably with it, but boy, you start going beyond that, it gets really finicky about the amplitude level. This is just really poor. I would have thought this meter would do much, much better. I mean, look at this. So just me handling the probe here, you can see how that's affecting it. Alright, so I've been sweeping through with my antenna and the RF generator, and I'm not really seeing any areas where this is really susceptible. Again, I have seen some meters fluctuate quite a bit in different modes, just doing a basic sweep with a little antenna like this. So this meter doesn't appear to be too bad. Currently I have the meter attached to my fluke reference. You can see we're outputting roughly 10 volts. This is with 1 volt applied. This is with 1 millivolt applied. Looks like it's fine. So currently I have both of these meters tied in parallel. I'm outputting a 100 Hertz sine wave, and you can see it has an amplitude of 100 millivolts. I've got both meters set for their millivolt range, and I'm going to increase the frequency, and let's just see where the 3 dB point is. So you can see roughly 3.33 kilohertz is the 3 dB point while it's in the millivolt range. Let's just try it in the volts range and see if that changes at all. And again, you can see I'm outputting roughly 1 volt, and we are again at 100 Hertz. So you can see roughly 3 kilohertz. So the KT6000 doesn't have a real high analog bandwidth. This will be with a 0.1 ohm resistor. This is a 0.5 ohm resistor. This is with 1 ohm applied. This is with 50 ohms, 100 ohms, 1K, and again this 1K is a 0.1% resistor. The 100 ohms was a 0.01%. This is with 10K, 100K, 1 meg, and this is with 10 meg. You can see it's not a very fast meter for selecting the auto range. Let's try the continuity mode. This will be diode check, and this is with a short and a single diode, 2 diodes, and 3 diodes is no problem. This will be a 150 picofarad. This will be 1 nanofarad. This is a 0.1. This will be 1 microfarad. 10 microfarads. And a 100 microfarad. Again, it takes it quite a while to get in. So again, for smaller capacitances, I normally would test these on a network analyzer. What I'll do is use this calibration board here to try to zero it out. So we'll select the rel. Now this is a 10 picofarad capacitor, and let's just see if it can pick this up. So it reads roughly 1 picofarad with a 10 picofarad capacitor. This is a 100 picofarad, and that's fairly close, about 108 picofarads. This will be 1,000 picofarads. So it reads a little high, but not too bad. I'm not sure how the one reviewer was getting down into the 1 picofarad range with it. Again, this is a 1 picofarad capacitor, and you know, this thing's just going to read all zeros. So I assume that they just received a better meter than what I got. So using our box, what we're going to do is apply a 2.5 volt reference. This is roughly 2.48 or so is what it works out to, and this will be a square wave, and there'll be no DC bias with this. So that is correct. Now what I'm going to do is add our DC bias, and we can see it's still reading roughly 2.48, and at DC volts it should also read roughly 248. So that is correct. Let's try it with the frequency input. So again, this will be AC coupled, and there's our 60 Hertz. And let's try it with our DC coupled. So it cannot read that. So unfortunately, this meter requires that the signal goes through the zero cross in order to read frequency. Let's see if that's the same in the millivolt range. Again, here's our 60 Hertz, and this will be with our DC offset. So this can read it. There's our 30, 15 hertz, 120, 240. So no problem there, but it can't do it in the AC volts mode. Of course, this should be 50%. It's no problem. One thing I don't like with these meters is when the probes are open, you can see it's reading the same value as what roughly the room temp is. So you don't really know if it's working or not until you actually change the thermocouple. And of course I can't do that with this box because I don't have access to the probe tip. I may actually have to run that out or something. But with the real thermocouple attached, you can see I've got it backwards, but it does change the value. So that seems fine. You can see I have my new ESD gun out. And again, this will output a DC voltage as well. So what we're going to do is adjust the DC voltage. But before I do that, I noticed something. Currently I have the Bryman off. I'm putting out roughly 240 volts right now. I'll go ahead and turn the Bryman back on. And you can see our 240 volts. Now watch what happens when I turn this meter off. Look at this. It's dragging down our power supply. So what I'm going to do is adjust our power supply off, and we'll disconnect the output. And let's just select this thing to ohms mode. Yeah, so it doesn't make a whole lot of sense. 10 meg, that's not much of a load. And if we look at the Bryman, it's basically an infinite load. So it's pretty bizarre. So in DC volts mode, you can see it's reading roughly 11.6 meg. And when it's off, it's reading roughly 10.6 meg. So you can see I've placed the Bryman in series with this meter, and the Bryman is looking at the current then through this meter. So let's go ahead and we'll turn on the power supply. Wow, there's a milliamp right there. Somebody had asked me if this UT181A is now my primary bench meter, and I explained it wasn't. This BM869S is still my favorite meter out of all the ones I've purchased. This Unity 181A is looking at the voltage drop across this meter, and the Bryman is looking at the current through it. So let's go ahead and we'll increase the voltage. Go to voltage mode, you can see 45 volts. Current drops to nothing. Shut it off. Look at that. Let's take this thing apart real quick. You see I've got our TP194 hooked up. Again, this is currently set to DC volts mode, and you can see the meter still works fine. It does have some leakage problems in the resistance mode or something. This meter was damaged when I hooked it up to the 230 volt supply, of all things. So when I have the meter in the off mode, again we're drawing our roughly 8 milliamps right now, you can see there's roughly 3 volts across our 2 clamp transistors here. And I'll bet you if we are in the millivolt range, yep, you'll see the same thing. Of course, there's our 3 volts. And if we go to our DC volt mode, I expect this is now going to be off. Right, so it switches out this clamp when it's in the voltage mode, and I'm assuming that's because the voltage is being seen, yep, right there. So 45 volts to the string of the high voltage resistors here. So when they are in the DC volt mode, this protection circuitry is switched out. Yeah, I guess they're trying to protect the meter when it's in the off mode from transients, but yeah, I don't know. So as long as I have all 4 meters out, we'll just hook them all up in parallel. I'm at it. This is what the backlight looks like. And this is with the lights off. One LED, it's got a definite hot spot right here, but it's not that bad, definitely usable. So let's just see, we'll increase our voltage. And we can see the lightning bolt is being displayed on the TPI. We definitely have the high voltage symbol on the unit T. This is roughly 770 volts. And that is this KT6000 that's beeping right now. You can see all four meters are reading roughly 1004 volts. No problems at all. Okay, I have the meter connected to our transient generator. I'm just going to output a 220 volt rectified signal. And we can see it's reading roughly 121 volts AC and about 240 volts DC right now. What I'll do is rotate the knob again through all the different modes except for the current. Of course, we have to disable the voltage for the current modes, and we'll re-enable it. And there's our 240. Well, that's interesting. Well, look at this. I think we damaged our meter. This should be reading about 120 volts right now. You can see it's only reading 1.3 volts. Turn the AC off. About 4.4. Turn it back on. Wow. That is bizarre. Let's just try it in DC volts. Now we'll go back to AC. Well, that's pretty bizarre. So just going to the DC volts mode and then back to the AC volts mode, it can't read AC again. Select the DC volts, reselect AC, and it reads a low value. Let's try inverting the polarity and see if that has an effect. There's our 240 volts negative. So there it works. Again, back to DC and back to AC. And we'll flip the voltage back around. There's our AC volts and DC. Oops. Yep. So I would say this is a bug in the meter. Let's go ahead and we will functional test it. At least make sure we didn't damage anything else. So we know the AC and DC volt modes work. That's correct. Let's try AC. Should be about 115. That's correct. And let's try frequency. That's correct. This is 50 ohms. 100, 1K, 10K, 100K, 1 meg, 10 meg, continuity test, and this will be a single diode, our 150 picofarads, here's our 1 nanofarad, and our 0.1 microfarad. And this will be our temperature sensor, and again that appears fine. So it doesn't look like we damaged the meter at all, but it definitely has a bug. I've never seen a problem like that with a meter. But again, it's $40 and you can see the internal construction is not the greatest. This is the TPI 194.2, and the test that I just performed where I was injecting the AC voltage into this is actually what damaged this meter. So yeah, I'm not very happy with this meter at all. Again, this should have been a lot better protected for the price that you pay. But I say that for this Unity 181A. Again, one hit with a grill starter took this out. So it's not always what you pay for. Some of these high-end meters just are not very good in my opinion. So you can see I now have the meter attached to our ESD gun. Again, this new gun will put out about a 15 amp peak pulse in under 1 nanosecond. And it has a decay roughly following the IEC standards. So I'll be applying 5 pulses of both a positive and negative transient in each mode of the meter. Alright, we'll go ahead and functional test it. Let's just start with temperature. That looks fine. This will be our 150 picofarads, 1 nanofarad, 0.1 microfarads, 1 microfarad, 10 microfarads, 100 microfarads, 0.5 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, and 10 megs. Continuity test. This is diode check with a short, and here it is with 1 diode, 2, and 3 diodes. I need to adjust this box. So this will be roughly 60 hertz. So yeah, the meter looks fine, no damage from our ESD test. Alright, you can see I have the meter attached to our transient generator. We have our high voltage probe attached to our oscilloscope, again to monitor the waveforms. Currently the scope is set for 500 volts per division, or 1000 volts peak. This is roughly a 100 microsecond full width half height pulse, and this will have a 2 ohm source impedance. Again, I'll be applying 5 transients, both positive and negative, in each mode of the meter except the current input. Alright, so I functional tested the meter. Looks just fine. And I've reset our generator for 1500 volts. See, this is roughly still 500 volts per division, or 3 divisions up. Alright, so the meter passes functional just fine. What I was thinking about is when I had this thing hooked up to our ESD gun and it was in the off mode and it enabled that transient protection, I wonder if they're not trying to protect the IC against ESD, although I'm surprised they just wouldn't switch everything out, but maybe it was something like that that they were concerned about. Anyway, I now have the transient generator set for 2000 volts. You can see it's still 500 volts per division, or 4 divisions up. That's it. Looks like the KT6000 passes functional just fine. You can see I've got the transient generator now set for 2,500 volts. Okay, that was 2,500 volts. So currently, you have the generator set for 3,000 volts peak. And this is exactly where this meter failed at. So again, we'll be applying 5 transients, positive and negative, 3,000 volts peak, 100 microsecond full width half height, 2 ohm source impedance. Let's see if this meter can outsurvive its little brother here. Alright, that's it. Let's just see if some basic functions work. So here's the AC volts, that seems fine. DC volts looks fine. It's with our 115 millivolt. This is our 10 meg. There's a 0.5 ohm. Continuity test. Single diode. Capacitive mode. Here's 150 picofarads. And this will be our thermocouple. Looks fine. So I'll go ahead and finish functional testing this, but it does appear that this meter survived where the ZT102 did not. So pretty impressive. Alright, it passes functional just fine. You can see I've got the generator reset. Scope is currently 2,000 volts per division, or 4,000 volts peak. Again, this will be 5 transients in each mode of the meter. 100 microsecond full width half height. 2 ohm source impedance. Oh, there it goes. Yep, so it's starting to break down. Let's just see if the meter is still functional. Oh, we don't have our DC. Dang, I turned it off. Yeah, looks like it's totally dead. So I took the meter apart. I've currently got our bench supply set for 3 volts. You can see as soon as I apply power, see the backlight LED comes on. This thing's drawing about 600 milliamps right now. So let's just have a look. Yeah, main IC's a little warm. That's not too bad. Oh, here we go. This is the serial configuration ROM. Yeah, that's definitely blown. My guess is the main IC is also gone. Wow. Yeah, about 80 degrees Celsius. So let's just check our clamp. Oh, look at this. So that diode is still okay. And wow, this one's okay too. So the little high-speed clamp survived this just fine, and you'd kind of think it would, because again, that only comes into play when you get into the millivolt and ohms ranges. We damaged the meter when it was in the volts mode, and that should all be switched out. So whatever was breaking down, it's something else. I suspect maybe the switch. Okay, I've got our transient generator set for a 4,000 volt peak right now. I'll go ahead and start it. Let's just see if we can see an arc on the circuit board. Oh yeah, right in the switch. Okay. Well, that's too bad. Alright, so you can see the meter is set to the AC volts mode. And again, we have the half cycle line simulator active. I'm going to be applying a single transient just through the standard leads, and let's see what kind of damage occurs. I can smell it, but not a real big bang. Let's try the milliamp mode. See how the small glass fuse does. See, I've changed it over to what is now the 10 amp fuse. And let's just try it again with the half cycle line simulator. So again, I'm sure that damaged the fuse, but I didn't see a whole lot of arcing outside of the case. Looks like it started to de-encapsulate the IC. The PTC still looks fine. Actually, so does the clamp. Wow. There's a lot of traces missing on that circuit board. I think this was our original breakdown for the AC volt mode. It was arcing up in this area here. So we can see this is the volt ohm mode right here. And this trace is just completely gone all the way back to here. So when I started looking at this meter, one of the things I was curious about was how much current this little shunt could actually handle. So I've got the big power supply back out. So the problem is we need a new fuse. Okay, we can see the shunt located right here, and this is our current. You can see I'm currently putting out 2 amps. So what I'm going to do is every 5 seconds we'll increase the current by 2 amps up to a maximum of 100 amps, and let's just see where the shunt opens up at. You can see the solder down here is starting to reflow. Connector here is actually reflowing as well. So there you have it. That was the KASUNTEST KT6000 True RMS meter. Comparing these meters, the KASUNTEST KT6000 is a 6,000 count. This Unity UT61 is 22,000 counts. The DT9939 from SEM is a 40,000 count meter. And then the Bryman BM869S is a 500,000 count meter. All the meters can read temperature except the UT61E. They all have a backlight except the UT61E. Both the Unity and the Bryman have a serial communications link to the PC. The SEM meter does as well, but it's a wireless connection, and the KASUNTEST has no way to log any data to the PC. So what I really don't like about this KASUNTEST meter is, first of all, that when it's in the AC volt mode and we're working with a rectified AC signal, and I switch it to DC and then back to AC, there's a 50-50 chance, depending on the polarity, that this thing may not read the AC volts again. So if I start out with the DC and I go to AC, you may not read anything, thinking the voltage is off or something, and then you go touching it. That could be a real bad situation. I don't know how they ended up with a bug like that. To me, that's just inexcusable. Most of the meters, like the Bryman and the SEM, will have an AC plus DC mode, and meters like the UT61, you would just do the calculation manually. But with this meter, you can't even do that because you can't rely on it. The only thing I don't like about this meter is the frequency counter requires that the signal goes through the zero crossing. So if I'm looking at digital signals, for example, where everything is referenced above ground, this can't read the frequency. The only thing I don't like about the frequency counter is it's limited to such a low frequency. Of course, the analog bandwidth of this meter is not the greatest either. For me, that's not too much of a problem because normally I'm using an oscilloscope if I'm working with very high frequencies anyway. Of course, this meter failed with a 4,000 volt transient. When we look at the UT61E, this would fail ESD. Of course, this meter has never been damaged. But, you know, I've spent a lot of time modifying this meter to harden it. I've also improved its temperature drift. I've added a backlight. You know, it's got better fuses in it. But you know, you look at the amount of time that I have invested into this and the cost of the parts, you know, this is not a $50 meter anymore. Looking at the SEM, this particular meter was damaged at 2,500 volts. But again, this meter has AC plus DC, it's a tri-display, it's 40,000 counts. So if I'm looking for a meter to basically replace my bench meters, which is what I'm doing with these higher end meters, this actually does a pretty decent job. And with Ruby Electronics selling this thing for $120, this was kind of a no-brainer. When I looked at my X-Tech equivalent of this meter, It by far has the worst temperature drift of all the meters that I've tested. I'm assuming that this SEM meter does the same. So then we get into the Bryman meter. Of course, this costs $230, but this is a whole nother class of meters. You know, this has all the features that I like. I love having these two temperature inputs. You know, the fact that I can do a difference on them. The UT181A also has that feature. And I've had this meter for coming up on 2 years now. I've been quite happy with it. Again, it's not the most robust meter, but it certainly is of the four that I'm showing here. And again, this meter survived the maximum levels I could put out with this transient generator, and that includes this half-cycle AC line simulator. So again, it's not the most robust meter of the ones that I've tested, but just having the features that I use, this has been a very good replacement for my bench meters. Well, I'd like to welcome all you new followers. Looks like we're getting very close to 2,000 members now. And I think that's going to be it for this video. Till the next meter. Later.